A 10 kilogram block rests initially on a table as shown in cases 1 and 2 here. The coefficient of kinetic friction between the block and the table is 0.2. The block is connected to a cord of negligible mass, which hangs over a massless frictionless pulley. In case 1, a force of 50 newtons is applied to the cord. In case 2, an object of mass 5 kilograms is hung on the bottom of the cord. Use g equals 10 meters per second squared. Calculate the acceleration of the 10 kilogram blocks in both cases. Which block has a larger acceleration? So these two cases might look almost the same, as the weight of the second block is also equal to 50 newtons, given the constant of gravity they give us here. But they are not actually the same, and you'll see why in a second. So over here are some free body diagrams for both case 1 and case 2. So let's start with case 1, the simple one, as it only has one object. So from the free body diagram, we can say that the force minus the force of friction must equal the mass times acceleration. This is simply Newton's second law, which says that the net force is equal to the mass times the acceleration. So we know that the force of friction is equal to the coefficient of kinetic friction times the normal force, which equals the coefficient of kinetic friction times the mass times the gravity. So we can substitute that in. And then now we just need to simply solve for the acceleration. So the acceleration is just simply this whole quantity here divided by the mass. Now all we need to do is plug all of our numbers in. The pulling force is 50 newtons minus the coefficient of kinetic friction of 0.2, the mass of 10 kilograms, the acceleration of gravity of 10 meters per second squared, and then we're going to divide all of that by the mass of 10 kilograms. So you get that the acceleration is equal to 3 meters per second squared. And that is for case 1. So for case 1, the acceleration is equal to 3 meters per second squared. Now we need to figure out case 2. Not going to write this yet. So let's look at our free body diagrams. For the first object, the block on the table is still the same. You have the tension minus the force of friction is equal to the mass times acceleration, which is the same thing as this. And now in the second one, we can derive another equation. We know that the weight of the second object, or its mass times gravity, we're going to say capital M for this one instead of lowercase m. We subtract the tension force from it that's pulling up must equal the mass times acceleration. And the acceleration is towards the downwards direction, so it's negative. So if you cancel that out, this equation, putting the weight in front makes the equation more convenient to solve. Oh yeah, about this, this is supposed to be the other mass, capital M, not little m. Be careful, you don't want to make those mistakes. So now we can just solve for tension and then substitute that value into the second equation. So from this equation, we know that the tension is equal to the mass times acceleration plus the coefficient of kinetic friction times the mass times the gravitational acceleration. Now all we need to do is plug this back into the second one. Minus mass times acceleration minus the coefficient of kinetic friction times the mass times the acceleration due to gravity. And then we're going to set that equal to the capital M times the acceleration. Now all we need to do is solve for the acceleration. And we can do that using a little bit of algebra. So if we move this over to the other side, then we can factor out gravity. And then we're left with capital M minus the coefficient of kinetic friction times little m is equal to, and on this side we can factor out the acceleration times capital M plus little m. And then now we just simplify this equation here, to get that the acceleration is equal to the acceleration due to gravity times capital M minus the coefficient of friction times little m, all divided by capital M plus little m. And now we need to just simply plug everything in. This is equal to the gravitational acceleration of 10 meters per second squared times capital M, which is the mass of the little block actually. Should have actually been reversed, but it doesn't really matter. 5 kilograms minus the coefficient of kinetic friction times little m, which is actually the big block of 10 kilograms. And now we're going to divide that by the total of the two masses, which is capital M, or the small mass, plus little m, or the big mass. And now if you simplify this, you should get that the acceleration is 2 meters per second squared. So I'm going to rewrite that up there. So for case 2, the acceleration is equal to 2 meters per second squared. And so the block in case 1 has a greater acceleration than the block in case 2. And now if you think about this kind of makes sense. Since both of them, they're being pulled by the same force and they have the same force of friction. The only difference is that that force now has to accelerate more mass in case 2 than in case 1, as you have the additional 5 kilograms that you have to accelerate as well. And that is why it has slightly less acceleration, because it has more mass. And that is how you would solve this problem here.